In chapter 6, we shall learn about surfaces. Surfaces are the subspaces of E3. So, they have the representation or equation in 3 variables x, y, z, but we can also represent these surfaces by the independent 2 variables, that is called parameters, and this parametric representation was introduced by Gauss, a German mathematician. So, in this module we shall learn about the parametric representation of surfaces and the curvilinear coordinate system on surfaces, and also the angle between two vectors. That means, how to calculate the angle between two vectors between the curves on surfaces. Now, first we consider a function of 3 variables, and one variable is dependent on others. So, they can be written as f x y z equal to 0. That means, it is a function of 3 variables and it represents a surface, we know that one. Or we can express this f x y z equal to 0 in the following manner: z equal to g x y, y equals to h x z, x equals to g y z. So, by these 3 equations, this f x y z also can be expressed. That means, the 2 independent variables can be given to the equation so that it will determine the surface. So, surface is a 2-dimensional subspace in E3. Let us consider an example. We take equation of a sphere with center at origin and radius a is x square plus y square plus z square equal to a square. Though it is written as a function of x, y, z, but we are denoting this one by S2 because it has 2 independent variable and the dimension of this space can be expressed in S2. Now, this x square plus y square plus z square can be written as z equal to plus minus root over a square minus x square minus y square. So, z is written as a function of x and y in the previous example. Thus, German mathematician Gauss introduced the parametric representation of surface. So, equation of surface given by Gauss is x I equal to x I u1 u2 I equals to 1 2 3. That means, u1 and u2 are the 2 independent variables by which the equation of surface is represented. These are the parameters by which the equation of surface is represented. So, we can write 3 equations: x1 as a function of u1 u2, x2 it is a function of u1 u2, and x3 as a function of u1 u2. So, equation 1 is giving 3 equations containing the equations with u1 and u2 as variable. U1 and U2 are known as parameters. Just I have mentioned. Let us consider this example. Suppose x1 is given as U1 plus U2, x2 is given U1 minus U2, x3 is given 4 U1 U2. Now, what does this surface represent? This will represent a hyperbolic paraboloid. If we just eliminate U1 U2, we get that this parametric equation represents a hyperbolic paraboloid. We consider another example, x1 equal to a cos U1 cos U2, x2 equal to b cos U1 sin U2, x3 equal to c sin U1. So, all the x1, x2, x3 are functions of U1 and U2, but x3 is only function of U1. And if we eliminate U1, U2, U3, we have the equation x1 square by a square plus x2 square by b square plus x3 square by c square equal to 1, which is the equation of an ellipsoid. So, all these surfaces are represented by parametrically by the equations given above. Now, a natural question arises that whether the parametric representations of a surface is unique. The answer is negative. Let us consider the surface which is represented by the equation x1 equal to V1, x2 equal to V2 and x3 equal to V1 square minus V2 square. And again, if x1 is considered as U1 cos hyperbolic U2, x2 equal to U1 sin hyperbolic U2 and x3 equal to U1, then both the equations are representation of hyperbolic paraboloid. So, the parametric representation is not unique, because just we have seen that hyperbolic paraboloid is represented in 3 parametric equations. So, we can say that the parametric representation is not unique. Now, from the equation given by Gauss, if we consider U1 equals to constant, we get U2 curve. If the constant is changed arbitrarily, we get family of parallel curves, they are called U2 curves. That means, if U1 is considered as constant, we are getting a family of parallel curves called U2 curves. Similarly, we can get family of parallel U1 curves if U2 remains constant. So, these U1 curves and U2 curves form a net on the surface and they form a curvilinear coordinate system on the surface. So, anything if we want to measure on the surface, we have to use this coordinate system, that is curvilinear coordinate system framed by U1 curves and U2 curves. For example, longitude and latitude on earth is the example of curvilinear coordinate system on the earth's surface, because any distance or anything we want to measure, we have to use the longitude and latitude for the earth surface. From the parametric equation of surfaces, that is xi equal to xi u1 u2, if we take dxi from the tensor, we have dxi is a contravariant vector and dxi can be expressed as del xi del u alpha du alpha, where alpha is running from 1 to. This alpha is called surface index. And again dxi can be also expressed as del xi del u beta du beta, where I is 1, 2, 3. Now, d square, anything if we want to measure on that surface, so d square equal to dxi whole square, and that can be expressed as del xi del u alpha del xi del u beta du alpha du beta. Alpha beta are the dummy index and the summation is done over this alpha beta. Now, if we denote del xi del u alpha del xi del u beta by a alpha beta, then d square can be represented by a alpha beta du alpha du beta. So, 2 is called the first fundamental form on surface and denoted by A. So, by using 2 we can find the arc length on a surface or any measurement with respect to curve can be done with this formula. A alpha beta is called the coefficient of first fundamental form, which is a covariant symmetric tensor of rank 2, because again it is a product of two partial derivatives del xi del u alpha del xi del u beta. So, A alpha beta is also a symmetric covariant tensor of rank 2. Now, let us consider for this example, and we are trying to find the first fundamental form for this surface. If x1 equal to u1 plus u2, x2 equal to u1 minus u2 and x3 equal to 4 u1 u2, we are going to find the value of A alpha beta and also the first fundamental form. From the formula A alpha beta del xi del u alpha del xi del u beta, where alpha beta is running from 1 to and I is running from 1 to 3, we have A11 equals to 2 plus 16 u2 square, A12 equals to 16 u1 u2, A22 equals to 2 plus 16 u1 square. So, d square can be expressed as 2 plus 16 u2 square d1 square plus twice A12 16 u1 u2 d1 du2 plus 2 plus 16 u1 square du2 square. This is the first fundamental form for this surface. So, in previous section of chapter 6, we have represented a surface parametrically and which is expressed as xi equal to xi u1 u2. That means, we have expressed a surface with respect to two independent parameters. We have also obtained the curvilinear coordinate system on the surface, and with the help of that coordinate system we can measure the distance between any two points on the surface or we can find the arc length by using the first fundamental form which is obtained in our previous section, that ds square equal to a alpha beta du alpha du beta. This is the first fundamental form by which we can find the distance on the surface. Now, in the next section, by using this first fundamental form, we shall try to find the angle between any two curves on the surface, and also we will find the angle between the parametric curves or the coordinate curves. So, let us define the angle between two curves on surface. Now, let us consider two arc lengths on a surface denoted by S1 and S2 with first fundamental form A. So, for a particular type of surface, the first fundamental form is unique. So, it can be expressed as d s square equals to a alpha beta du alpha du beta. Now, if theta is the angle between tangent vectors to these curves, then cos theta can be defined as a alpha beta lambda alpha 1 lambda beta 2. Now, what is the meaning of this lambda alpha 1 and lambda beta 2? A alpha beta is the coefficient of the first fundamental form. Just we have seen in our earlier section that A alpha beta is a covariant symmetric tensor of rank 2. Now, lambda alpha 1 are the components of unit tangent vector for the arc length S1, and lambda beta 2 are the components of unit tangent vector for the arc length S2. So, the angle between them can be written in this form, and as they are unit vectors, that means lambda alpha 1 and lambda beta 2 are unit tangent vectors along S1 and S2. So, there will be no denominator. So, cos theta is expressed in this way, where lambda alpha 1 is the unit tangent vectors for the first curve and lambda beta 2 are the components of unit tangent vectors for the second curve. Now, the important thing is to find the angle between two parametric curves. That means, the curvilinear coordinate system is consisted of two types of curves, U1 curves and U2 curves. So, we are going to find the angle between two parametric curves or coordinate curves, that is U1 curves and U2 curves. Now, for U1 curves, U2 is constant. Therefore, du2 is equal to 0. Thus, components of tangent vector along U1 curve will be lambda 1 1 lambda 1 2. So, these are the components of unit tangent vector for the U1 curves, and this one is coming to 1 by root a 1 1 comma 0, because as du2 is 0, du2 ds equals to 0 and d1 ds is 1 by a root a11. So, the components of the unit tangent vector along E1 curves is 1 by root a11 comma 0. So, just I have mentioned this one, that lambda 1 equals to d1 ds1 and that is equals to 1 by root a11. Similarly, components of tangent vector along U2 curve the same way lambda 1 2 and lambda 2 2, and this will becomes 0 and 1 by a root 2 2, because here d1 is 0. So, d1 ds equals to 0 and du2 ds is coming to the value 1 by root a22. Now, if alpha is the angle between two parametric curves, then cos alpha will be equal to a11 lambda 11 lambda 12 plus a12 lambda 11 lambda 22 plus a21 lambda 21 lambda 12 plus a22 lambda 21 lambda 22. And all these expressions, the other expressions for first one, third one and fourth one are 0, only the second expression has the value, that is a12 lambda 11 is 1 by root a11 and lambda 22 is root over 1 by a22. So, cos alpha is equal to a12 by root a11 a22. That means, angle between two parametric curves can be calculated by the fundamental metric tensor A alpha beta, where alpha beta is running from 1 to. So, if we just calculate A11, A22 and A12, we can find the angle between the parametric curves, U1 curves and U2 curves. Now, if the curvilinear coordinate system is orthogonal, then obviously alpha equals to pi by 2 and the value of a12 will be equals to 0. So, this is the necessary and sufficient condition for parametric curves to be orthogonal, that a12 equals to 0. So, we can say that necessary and sufficient condition for parametric curves to be orthogonal is a12 equals to 0. Now, let us check whether the curvilinear coordinate system is orthogonal or not for the following surfaces. We consider this surface x1 equal to u cos v, x2 equal to u sin v, x3 equal to c v, where c is a constant, and we will also see for the surface x1 equal to u plus v, x2 equal to u minus v, x3 equal to 4 u v. The first surface is a helicoid and the second surface is a hyperbolic paraboloid. So, we shall try to find that whether the curvilinear coordinate system is orthogonal or not for these two surfaces. So, for the first one, where the equation is given by x 1 equal to u cos v, x 2 equal to u sin v and x 3 equal to c v, if we calculate A alpha beta by the formula del xi del u alpha del xi del u beta, where alpha beta is running from 1 2 and I is running from 1 to 3, we have A12 equals to this expression, and if we calculate, we are getting A12 equals to 0. That means, for helicoid the curvilinear coordinate system is orthogonal. This is very important, that if the curvilinear coordinate system is orthogonal, we can measure the other things very elegantly. For the second surface, that is for hyperbolic paraboloid, we have x 1 equal to u plus v, x 2 equal to u minus v and x 3 equal to 4 u v, and if we calculate A12, we are getting 16 u v, and which is not equal to 0 unless u v equals to 0, but u v cannot be 0. So, A12 is not equal to 0. Therefore, the curvilinear coordinate system is not orthogonal. So, in last section of module 1 of chapter 6, we have learnt about the angle between two curves on a surface, and specially the angle between two parametric curves on that surface, and we have observed that the two curves will be orthogonal if A12 is equal to 0, which is the necessary and sufficient condition for the parametric curves to be orthogonal. With this, we end this module number 1 of chapter 6.